All right, today we're diving into something that's, well, it's pretty unsettling in the world of cybersecurity. We're talking about software and data integrity failures. This is what happens when the very code and data you're supposed to trust have been secretly changed, turning your own systems into a weapon against you.
And to really get why this is so scary, you just have to look at SolarWinds. I mean, this wasn't some flashy brute force attack. It was a betrayal. A completely legitimate signed software update became the Trojan horse for one of the biggest cyber espionage campaigns we've ever seen. It is the absolute nightmare scenario for this kind of failure.
So, yeah, that perfectly sets the stage for our first section, a breach of digital trust. This isn't just about a simple bug in the code. We're talking about a fundamental breakdown of our most basic assumption, that our software is what it says it is. So really, what happens when you can't even trust your own code? So what are we really talking about here? At its core, an integrity failure happens when a system just blindly trusts an update or a piece of data without checking where it came from or if it's been messed with. You know that little foil seal on a bottle of aspirin? If it's broken, you're not taking that pill, right? No way. Well, this is the digital version of ignoring that broken seal and swallowing the pill anyway.
Now, you might be thinking, hang on, isn't this just a supply chain attack? And that's a really good question. They're definitely related, but there's a key difference. A broader supply chain failure is about trusting the companies you get your software from. But A08, what we're talking about today, is much more focused. It's about checking that one specific file, that one update, that plugin, that chunk of data, right before you let it run inside your own four walls. It's that last critical checkpoint.
So, how does this trust actually get broken in the real world? Let's get into the nitty-gritty. We're going to look at the common patterns of failure. Basically, these are the playbooks that attackers use over and over again.
Okay, pattern number 1, the absolute classic, unsigned software and updates. You know how so many apps are set to auto-update? It's super convenient, right? But the problem is, when that app downloads a new update and has no way to prove it actually came from the real developer, it leaves the door wide open.
And the way this attack works, it's just brutally simple. Your device calls out to the server for an update. An attacker in the middle grabs that request and sends back their own nasty malicious file instead. And because your device never asks for a digital ID, a valid signature, it just says, "Okay, looks good to me," and installs the malware. And just like that, it's game over.
All right, our next pattern is, well, it's a lot sneakier. It doesn't target the software on your machine. It targets the factory where the software is actually built. We're talking about the CI/CD pipeline.
See, in this case, the attacker doesn't bother with the download. They go straight to the source. They find a way to break into the build server and inject their malicious code right as the software is being compiled. What comes out the other end is a perfectly packaged, trusted, and even digitally signed piece of malware that gets shipped directly from the developer to, well, to everyone. This is exactly how the SolarWinds attack went down.
And for our third pattern, this is where the data itself becomes the weapon. It's a tricky technique called insecure deserialization. It's like hiding a bomb inside a birthday cake. An attacker can hide executable commands inside what looks like just a normal piece of data.
Okay, I know this can all sound a little theoretical. Unsigned updates, deserialization. So in this next section, we're going to make it real. Let's look at some actual attack stories that turn this theory into a very, very tangible threat. So let's start with that last one. How in the world can just receiving a little bit of data, something your server does constantly, lead to a total takeover? It sounds kind of impossible, but believe me, it happens all the time.
Well, here's how it goes down. The attacker cooks up this special data object with hidden commands buried inside. When your application gets this object and deserializes it, which is really just a fancy word for unpacking it, the application gets tricked into executing those hidden commands. And this is the critical part. This can lead directly to remote code execution, giving the attacker full control of your server.
Now, if you're the type who likes to get technical, the security world has official names for these things. They're called Common Weakness Enumerations, or CWEs. You can see some of the big ones here. That's CWE 502, that's the insecure deserialization we were just talking about. And CW 494, that's our classic unsigned update attack. These are basically the technical fingerprints that these attacks leave behind.
And here's another one. I guarantee you this happens every single day. A developer is in a rush, they need a library to get their job done, and instead of going to the official source, they just grab it from some random website. They install it, and bam, the package was a Trojan horse. It wasn't just code, it was a backdoor that now has access to the entire company's development environment. Okay, that's enough doom and gloom. We've seen how bad it can get. Now let's flip this around and talk about how to actually fix it. It's time to build our integrity checklist. This is how we can start to rebuild that trust in our digital world.
So here's our game plan. First things first, you've got to put a lock on everything. Digitally sign all your updates, your packages, you name it. But, and this is key, you also have to actually check the signature before you use it. Second, protect the factory. Lock down that CI/CD pipeline with strong security. Third, for anything you pull from the outside world, like scripts from another website, use tools like sub-resource integrity to make sure they haven't been tampered with. And this is a big one. You have to adopt a zero-trust mindset for data. Treat all incoming data as hostile until you can prove it's safe. Finally, you have to be watching. Keep an eye on your critical data for any weird or unauthorized changes.
So, why should your boss care about all this technical stuff? Let's talk about the bottom line, the ultimate price a business pays when this goes wrong. Let's just start with a number. OWASP gives this category a weighted exploit score of 7.11 out of 10. And let me tell you, 7.11 is high. That means attackers love these kinds of bugs. They're often easy to find, and they work really well.
The impact on the business is just brutal. We're talking hidden backdoors in software that you paid for and thought you could trust. Think about your critical data, financial records, customer info, just silently getting corrupted, and you have no idea. A single lapse can lead to a massive, company-wide compromise. And maybe the worst part? It completely shatters trust. If you can't trust your own data and logs, how can you possibly figure out what happened after an attack?
And that really brings us to our final thought. We all get physical security. You wouldn't leave your house without locking the front door, right? It's just common sense. So the question I'll leave you with is this: what are the locks you're putting on your code?